Hi. So in this week's lab, we are given a star's position data as it orbits a black hole, and we are asked to use that and a list of other variables for the given situation to find the mass of the black hole. So first, what is a black hole? Dictionary.com tells us that a black hole is a region of space with a gravitational pull so large that no matter can escape it. NASA says that the gravitational pull is so strong that not even light can get out. So the goal of this lab is to overall expand our knowledge on black holes and apply some concepts that we have already learned to extract the mass of a black hole given certain pieces of information. So what we are given is the star's mass, 1.989 e to the 30 kilograms, the star's position data as it orbits the black hole's position, which is 4 e to the 10, negative 1 e to the 10, and 0 meters, and the time, which is 1 day. We are also told to assume that the only force acting on the star is the gravitational pull from the black hole. Using Newton's second law, force is equal to mass times acceleration, and or delta P is equal to F net times delta T, and the law of universal gravitation, which is force is equal to constant g times mass 1 times mass 2 divided by r squared, and then multiplied by the unit vector of r, we can edit the starter VPython code we are given to help us solve for the mass of the black hole. Now let's discuss my code. For my code, I first went through and updated the initial conditions given to me to work with. After that, I edited the initial and final velocity, then the initial and final momentum, and finally defined the net force in terms of dp dt, as well as the perpendicular and parallel components of the force. Now the reason why I can update all these lines and run them to find values is because my code is pulling the star's position data from the file I was given and applying Newton's second law to solve for the velocities, momentums, and the net force components in terms of dp dt. My last line was my application of Newton's universal law of gravitation to define the mass of the black hole. You can see that here. I set the mass of the black hole equal to the magnitude of the perpendicular component of the F net force times r mag squared, which r mag is equal to the magnitude of r, which is the star's position minus the black hole's position, and then that's divided by the constant g, which is also then divided by the mass of the star. With this, I was able to find that the mass of the black hole is 3.56 e to the 31 kilograms, which turned out to be correct. Overall, the code does 4 actions that helps me get to my answer. 1. It updates the x and y components of the velocity. It updates the momentum vectors, calculates the parallel and perpendicular components of the force as well as the net force, and finally, it updates the position of the star. Here's what my code looks like when I run it. The blue arrow is the perpendicular component of the net force, the black arrow is the parallel component, and the yellow arrow is the total net force inwards from the curvature of the star's path of motion around the black hole. One way to make sure that makes sense is to think about a situation involving trajectories and the direction of net forces that we already are familiar with. We know that when an object has orbital motion, the path it creates is also known as a kissing circle, and we know that the net force of the object is always pointing towards the center of the kissing circle. So here it makes sense that the total of the parallel and perpendicular forces acting on the star as it orbits the black hole points in the direction of the black hole, which is the center of the orbit. Finally, we are challenged to think about 2 questions. First, what is the difference between F net and its parallel perpendicular components and delta P delta T with its corresponding parallel and perpendicular components? So in order for F net or any component of F net to be equal to delta P delta T and its components, the net force and the mass must be constant. If they're not constant, then the force is equal to dp dt, which is the derivative of time and momentum. Here's to find what is actually a cause and effect relationship between force and dp dt. Force causes the change in momentum. Another point is that dp dt can be determined by observing the star's motion, whereas the net force is found by adding up the forces that are acting on the object. It cannot simply be observed. The last question is asking whether or not a new black hole could exist in this scenario with all else the same and have a different mass. The answer is no. Since the motion of the star remains the same and only the force acting on the star is being done by the black hole, then the new black hole would have the same mass as the original, and I would not be able to tell the difference between them. So to sum up this lab, I applied Newton's second law and universal law of gravitation used by the position data of an orbiting star around a black hole to find the mass of the black hole by modifying a starter code and tracker starter code in Python that pulled data from the star's position file. I then addressed 2 questions expanding on the relationship between the net force and the change in momentum in respect to time, as well as why the mass of the black hole could not be different in order for the star's motion to be the same. So that is my lab, and thank you for listening.